Mathematics is fun.
Mathematics is fun. And do you love mathematics?
Yes, miss.
Come on, let me hear you say it.
Yes, miss.
I love mathematics.
I love mathematics.
And here we are here to fill our minds, which we can call a garden, with thoughts and facts and generalizations about mathematics, okay? So we're going to be thinking, and as I say, as a man thinketh, so is he. So we're going to be thinking and processing mathematics all along, okay? Because mathematics is going to help us, whether it's at home, whether it's at work, or generally going out there in the society. So mathematics has got to be fun, and let me hear you. You are going to love mathematics. Say, I love mathematics.
I love mathematics.
Good. Now, in the past, we looked at sets and we looked at measurement. Now, today we want to conquer some other topics. We're going to look at a new topic called algebra. And in algebra, we're going to look at something called indices. Now let us say I have x and I have a little 2 up there. What do I call this entire thing?
X squared.
X squared, and there's a name we can give to x squared. It's a 4-letter word and begins with T. Juliana? Alia, would you like to help her? Yes, Jonathan?
It's a term.
It's a term. Very good. Now let us try to identify the different parts of this term. The 2, the x is looking up to the 2. So we can call the 2 the
Exponent.
exponent. Very good. We can also call the 2 the power. And there is one other name we can give to the 2.
Index.
Index. I have some brilliant students here. These are all distinction students, right?
Yes, miss.
Good. So here we have the x looking up to the 2, and the 2 can be referred to as the exponent or the power or the index. Now if the 2 can be considered any one of these, what do we call the x?
The base.
X is called the base. Now we will be dealing mainly with powers or index or exponent. Good? That's why we have our topic indices. And we'll be looking at different operations, and we'll be coming up with generalizations or rules. Now let's go. Operation of multiplication in all of these here. Here we're using terms with bases and exponents. Good. Now I want you to simplify number 1. Let me see what your answer is going to be quickly. What did you write?
X to the 4th power.
X to the 4th.
Y to the 7th.
Y to the 7th.
Z to the 2nd.
Z to the 2nd. Did you get it, Juliana?
Yes,
what about you, Lisa?
Yes,
Good. Try number 2 for me. What did you get here?
A, B cubed and C squared.
A, B cubed, and C squared. All those who have it, just raise your hand for me quickly. Beautiful. Third one. Yes, Ria, what did you get?
P to the fourth power,
P to the fourth,
Q,
Q,
and R to the fourth.
R to the fourth. Now let us examine all three of them together. We have x to the fourth by y to the 7 by z squared. And what we got here is x to the fourth, y to the 7, z squared. All we see missing is this multiplication sign. And even though it's not here, it's understood that it's there. So basically what we did for these three is remove this sign and rewrite everything else. And if I give you 42 others like this is the pattern that we'll take. So we're going to use x to the m and y to the n to come up with a little rule for when we have operations like these. Good? So we're starting over here. So what should I put between these two?
Multiplication sign.
Multiplication sign. When x to the m is multiplied by y to the n, what will I have?
X to the m, y to the n.
X to the m, y to the n. And it's always like that. As long as the terms are not alike, we can't simplify them any further. They have to stay separate. Okay? Good. So under, you at the bottom there, in your book, put in the generalization. When the bases are different and we're multiplying, everything is retained. We only ignore the sign here. Now let us imagine we have x squared multiplied by y squared. Here we have a cubed multiplied by b cubed multiplied by c cubed. And here we have p to the fourth by q to the fourth by r to the fourth. In the first set, what do you observe?
That the powers are similar.
The powers are all the same. Are the bases alike?
No.
No, the bases are different. The only difference is the powers are the same. When we simplify this, what would it look like across there? Solve it in your book quickly and let me see. Yes, Jonathan, what you got?
X square, y square, and z square.
You got x squared, y squared, and z squared. So he followed the first set of examples we did. He eliminated the multiplication signs. So that's one step. Can we go a further step?
Yes.
Yes, we can go one step further. And in the next step, what are we going to manipulate?
The squares.
The squares or the power. Kiran, tell me what should I do next?
Which it should be x, y, z,
X, Y, Z,
all square.
all squared. Okay? The 2 is common to every one of them. The square is common to every one of them. So we group the terms and we factor. We can say we factored out the power. Okay? Complete the second and the third. But you can look at the second and the third and tell me what the answer is going to be. What is the second one going to be?
A, B, and C in
A, B, C
brackets.
in bracket
All
and
cubed.
all cubed. And here we're going to have
PQR.
all to the
Fourth
fourth
power.
power. Now remember at the bottom we came to a conclusion. Now we're using x and y again. And we're using m. We have to get the same. It has to be the same. The power has to be the same. Complete the statement for me. So we're generalizing. Make sure you have your tree, and then we come to a conclusion. The bases are different, but the powers are the same. What happens in the end? Yes, Rhea, what did you write?
xm multiplied by ym is equal to xy
xy
in brackets
raised to the m power.
raised to the m power.
So here we have a generalization. The bases are different. We're multiplying, but the powers are the same. So we group the bases and we raise them to the same power. So that's our second little generalization. Okay? Good. Any questions? Now let us go back to this original term that we have. X squared. What does the little 2 tells us? It tells us something. It gives us a message. Every time we look at the 2, it tells us something. What does that 2 tell us?
X multiplied.
Multiply by itself 2 times.
How many times the base must be multiplied by itself? So x squared is the same as x multiplied by x. And how many x's are you seeing there being multiplied by itself? 2. So if I have p to the 5th power, that means I'm going to have how many p's when I expand?
5.
So I'm going to have 1, 2, 3, 4, 5. Okay? Everybody agree?
Yes, miss.
Now let us look at our first set of multiplication. We have x squared is being multiplied by x multiplied by x to the 4th. Now what do you notice about our bases across here? They are all the same. And if you see no numeral up here, it's implied that what numeral is there?
1.
1 is here. Now we want to simplify this here. What will be our answer? Now let us expand it. This one here means x is being multiplied by x, multiplied by another x, multiplied by, how many we having from this one?
4.
So we have 1, 2, 3, 4. How many x's do we have in all?
7.
7 x's. 2, 3, 4, 5, 6, 7. So that means that if we have x by x by x all the way and we have 7 of them, when we're ready to write it, it should be x raised to the 7th power because we have 7 of them here being multiplied by itself. Now let us compare that 7 with these indices that we have up here. We have a 2, and we have a 1, and we have a 4. And what do you notice when you compare the 7 to these 3? Alia?
Let's say I have to add them to get a 7.
When you add these 3, you get the same there. So instead of expanding these to get x to the 7, what could we have done instead, Lisa? Just simply add the powers. So we're going to take 1 base, x, and then we take the powers, 2, 1, and 4, and we end up with x to the 7th. And we could only have done this because a special condition existed. What is that condition?
Similar base.
All the bases are the same. Very good. Now in 2 and 3, the bases are the same. What should be the answer here when I simplify? For the second one.
18, 11 power.
A to the
11 power.
11 power. Now let us don't jump it. How did we get 11? A,
And then we add the bases.
and we add the indices, which are 4 to the 2 plus the 5. 5 and 2, 7, and 4 would give us 11. And the last one would be
Set to the 9 power.
set to the 9th power. And if we had B, or we had a C, or we had a Q, we would have taken the same approach. So now it's time for us to conclude based on what we found here. And we're going to use X and M and N to make our generalization. So we're saying X is the base, and it's X to the M by X to the N. What do we do when we get across on the other side?
X
We
equals
add the
M
power.
plus N.
Across on the other side, we'd have X to the M plus N. Now I want somebody in words to tell me what is happening here. When the bases are the same, you add the power. There's some, yes,
When the
Julia?
bases are the same and you're multiplying, you
That's
add
the
power.
key. When the bases are the same and you're multiplying, you add the powers. Okay? And this represents that. So take your third little generalization or rule down. X to the fourth is raised to the second power. So we have one power being raised to another power. Now this little 2 tells us what? That little 2 tells us something. It tells us what? What does it indicate to us? Yes, Jonathan?
That X to the full power must be multiplied by itself.
That X to the fourth power must be multiplied by itself. So we have X to the fourth multiplied by X to the fourth. Now remember the last little rule we came up with? That when the bases are the same and we're multiplying, what do we do with the powers?
Add.
We add. So we have X to the 4 plus 4, and we end up with X to the 8. Now I want you to look at the 8 and look at this 4 and this 2. See any similarity? Any idea comes to your mind? Yes, Juliana?
You can multiply the 4 by
We
2.
can, very good. We can simply multiply the 4 by the 2 to get the 8. So when a power is raised to another power, to simplify, we multiply the 2. So the other approach we can adopt is X to the 4 by 2, and we end up with X to the 8th power. So you now are going to use x, m, and n and come up with your rule here. Now. So here, without expanding and all of that, what would be my answer here? In this, what would be my answer in this second one?
P
to the
21 power.
P to the 21st power. So we simply multiplied. Ria, what did you get as your fourth rule?
M X
Yes, on let's go. X
M
raised to the m power. Close. Go on.
raised to the n power,
Raised to the n power
which
is equal to
x
x
m multiplied by n.
m multiplied by n. Or we can say mn.
Mn.
Right. Good girl. Good. So we generalize here. When a power is raised to another power, we simply multiply. So that's our fourth little rule. And if you notice, all we were doing here was multiplication. And then you see multiplication is associated with which other operation? Division. But when the bases were the same and we were multiplying, what did we do? Added. Okay? Good. Any questions? No questions. Certain? Good. Now let's proceed. So we were multiplying all along. Now we have x to the fourth is being divided by y to the second. In our second case, we have a to the seventh is being divided by b to the third. So the first question you should ask yourself, are the terms or the bases the same? We have an x term here and we have a y. X to the fourth, y to the second. Here we have an a to the seventh and a b to the third. Can we simplify? Are the terms the same? You question yourselves, are the terms the same? How far can we go when we simplify? So because the terms are different in this case, when we come across here to put our solution, write it for me. Come on, Kieran, put your answers on the board. Thank you, Kieran. Everybody agree with Kieran?
Yes, miss.
So we can't go any further. We bring back our x to the fourth divided by y squared, full stop. We can't simplify any further because the bases are different. So again, we're going to come up with our little generalization here. We're going to use our x and our m, our y and our n. Go ahead and fill in the sign, equals, and put the solution. Here,
Division sign.
the division sign equals
X to the m power
x to the m power
divided by y to
divided by y to the
the n.
n power. So when we're dividing and the bases are different, we basically bring back the same across on the other side. It doesn't change. Okay? So that's our first one for division. And what do you notice when you compare that to multiplication? Remember we did multiplication with something like that? And when you compare the two, what's the only difference?
Same.
The signs. Now let's follow the same pattern again. Yes, Matthew, what did you get for the first one?
A all upon B
A upon B,
to all to the fourth power.
all raised to the fourth power. And let me hear what you got for the second one.
X all upon Y.
X all upon Y,
all to
close
the
bracket, raised to the
seventh.
seventh power. And if we were to do 50 more like these, we'd come up with the same answer, similar answers. So I want you to write your statement at the bottom. Your concluding statement. And I see we are having here x to the m divided by y to the n would give us x divided by y all raised to the, yes, x to the m divided by y to the m would give us x over y all raised to the m power. Similar pattern as in multiplication, the only thing the sign is different. So that was our second case. In our third case, we have a to the fourth is being divided by a square. Now what I want you to do is to expand a to the fourth over expand a square. And cancel off. And let me hear what you come up with. Lisa has 1, 2, 3, 4, 1, 2. Did the others get that?
Yes, miss.
Good. Then the next thing I saw she did was she said A into A1, A into A1, A into A1, A into A1. And then she had 1 by A over 1 by 1. When 1 by 1 is multiplied, what we get?
1.
1 by
A.
A by A,
A square.
A squared. 1 by 1,
1.
and A squared upon 1 is the same as
A square.
A squared. So we have a 2 here, we have a 4 and a 2. How could we have moved from here to there?
Subtraction.
Subtract. Subtract what?
The 2 from the 4.
The 2 from the 4.
The lower power from the higher power.
Now let's go again. Let's see if we're going to come up with the same thing. The second one. We have b to the 7th is being divided by b to the 5th. Expand them again and do your cancelling off and tell me what you came up with. Yes, Alia. You expanded how many bees you had on top?
7.
You had 7. 1, 2, 3, 4, 5, 6, 7. At the bottom you had
5.
1, 2, 3, 4, 5. What did you do after that?
Just divide it,
Mm-hmm.
and then you will end up with b square.
So how did you go about doing your division?
Let's cancel.
You cancel out b's. So 1 at the bottom will cancel out 1 on top. So we're taking out the 5 at the bottom with the 5 on top. And you had 2 b's remaining. Good. So you ended up with b by b, which gave us b squared. And when we compare 7 and 5 to 2, what could we have done instead? Subtract. And why could we have subtracted? What condition is present for us to subtract?
Division.
Division. But there's something else.
The bases are the same.
The bases are the same. That's the key. The bases are the same. We're dividing. Okay? So the first thing you're going to do, let us put the alternative here. This is the same as a to the 4th take 2, and we have a square. And here we have b to the 7th take 5, and that would give us b squared. Now, from whatever knowledge you would have gotten here, I want you now to put the last rule together. Let us generalize and come up with a rule. What this is telling you. Give the interpretation of it. Yes, Lisa?
When the bases are the same,
You
you
have to
divide it.
speak up, speak up.
When the bases are the same,
When the
you
bases are
divide
the
it,
same,
you minus the power.
and you're dividing, you subtract the powers. Okay? So that was our third. Now let us look at this. We just learned that when the bases are the same and you're dividing, the powers are subtracted. So we have x to the 4th is being divided by x to the 4th. And if we expand them, we'd have 4 x's on top. And we'd have 4 x's also at the bottom. And we know that if we do this, we would have 1, by 1 by 1 by 1 over 1 by 1 by 1 by 1. And that would give us 1 over 1, which is the same as 1. But then we just learned that when the bases are the same and we're dividing, what do we do with the powers?
Subtract.
We subtract. So x to the 4 take 4 would give us what?
X to the 0.
X to the 0 power. And what did we do? Because it's the same thing we're working with. Here, when we expanded it, we came up with 1. And when we did it using the law, here we came up with x to the 0. Now let's try another set. Let us say we have p squared divided by p squared. If we expand that again, we're going to have p by p over p by p. P into p1, p into p1, p into p1, p into p1. So we have 1 by 1 over 1 by 1. That would give us a 1 over 1, which is 1. If we use the rule, we'd have p to the second take 2, and that would give us p to the 0. And if we take another set, we go over and over and over. The same pattern continues. So we can look at these two and draw a conclusion. What conclusion can we draw? Alia, would you like to tell me?
Is anything raised to the 0 power is 1?
That anything raised to the 0 power is 1. But I want you to first draw the conclusion between this and that. Ria, what do you think? What do you think if I want to write these two as a statement? What can I write? Jonathan, you want to tell me?
When the powers are similar, or when the bases are similar, you just subtract the bases.
But now
They
we're
have
looking at x to the 0 and we're looking at 1. Juliana? What conclusion that we can come to where with x to the 0 and the 1? Matthew?
When we have x is 0, it's the same as 1 because the x has no power and it's a single base.
The bases are the same. We can come to the conclusion that x to the 0 and 1 are the same because we use the same terms to get our answers. So x to the 0 is equal to 1. And here we can write p to the 0 is equal to 1. And if we do 10 more, we're going to write them the same way. So, because we can write this, we can write p to the 0 is 1, x to the 0 is 1, y to the 0 1, b to the 0 is 1. We can come to a general statement now. And who would like to tell me what a general statement is?
Anything raised to the 0 power is 1.
Anything raised to the 0 power is 1. Anything, anything, anything? What about 0? 0 raised to the 0 power. Is it equal to 1?
No.
No, it's not equal to 1. Because remember 0, we don't know 0. You know what nothing is? No. And you have nothing raised to the nothing power. 0 raised to the 0 power. When we have a case like this, we say it's undefined. This is the exception. Any symbol or numeral, you just raise it to the 0 power, it's always 1. Always. Except when 0 is raised to the 0 power. In this case here, our answer is undefined. Okay? Here it's defined, it's 1. Here it's defined, it's 1. And so in the other cases. But in that case, it's not defined. So we say it's undefined. Any questions? I see Alia smiling. I caught her with that one. Good. Now let us we started off with indices, and we did 4 different ways in which we can show multiplication. We say that when the bases are different, all we simply do is to group them back without the multiplication sign. When the bases are different but the index is the same, or the indices are the same, we group them and raise them to the same power. When the bases are the same and we're multiplying, we simply add the powers. And when a power is raised to a power, we multiply. And then we went down to division. We took our terms and we came up with 4 different ideas when we divided. If you're dividing and the bases are different, we simply group them and show division. When we're dividing, you have different bases, but the powers are the same. We group them again, showing division, and we raise them all to the same power. Anything raised to the 0 power is equal to 1 with the exception of 0. 0 raised to the 0 power is undefined. And the last one was, if you're multiplying terms such that the bases are the same, we simply subtract the powers. Now, I want you to go out. I already know that you're distinction students. And I want you to go out there and I want you to be ambassadors.
When you divide it,
Said multiply? Sorry. Now let us do some revision. Look here. Lesson 20, Algebra, Indices. In this lesson, we will apply the rules of indices to manipulate algebraic expressions with positive indices. Here are some key points. The word algebra is used to describe various abstract mathematical topics. The symbols of algebra include numbers, letters, and signs that indicate various arithmetic operations. Mathematicians consider algebra as a set of objects with rules for connecting or relating them. Compare and contrast. 3 cubed by 3 squared is equal to 3 by 3 by 3 by 3 by 3 by 3, which is equal to 3 to the 3 plus 2 equals 3 to the 5th. X to the third by x squared equals x by x by x by x by x by x equals x to the third plus 2 equals x to the 5th. X and 3, the base, 5 and 5, the index. Let us look at x squared. X to the second power is read x squared or x to the second power. A power is the product of a number multiplied by itself. X squared is the product of 2 factors, each of which is x. X squared is equal to x times x. The index or power or exponent tells us how many times the factor will appear in the repeated multiplication. When the basis x squared by y cubed equals x squared y cubed. In general, x to the a by y to the b is equal to x to the a y to the b. When the bases are different, x and y. When the bases are alike. 3 cubed by 3 squared equals 3 to the 3 plus 2 equals 3 to the 5th. X cubed by x squared equals x to the 3 plus 2 equals x to the 5th. In general,
x to the a by x to the b equals x to the a plus b. When the bases are different but the indices are alike, x squared by y squared equals xy all squared. In general, x to the n by y to the n equals xy raised to the n. Division. X squared divided by y squared is equal to x over y all squared. In general, x to the n divided by y to the n equals x over y raised to the n. When the bases are different but the indices are alike. When the bases are alike. 3 to the third divided by 3 squared equals 3 to the 3 take 2 equals 3 to the 1. X to the third over x to the second equals x to the 3 take 2 equals x to the 1. In general, x to the a divided by x to the b equals x to the a take b. Example 1, x to the 6 by x to the 4th divided by x to the 3rd is equal to a x to the negative 7, b x to the 6, c x to the 7th, d x to the 13th. This question was taken from the National Grade 9 examination in 2006. The answer is C. X to the 6th by x to the 4th divided by x to the 3rd is equal to x to the 6 plus 4 take 3. Power of a power. X to the 2nd raised to the 3rd equals x to the 2 by 3, which is equal to x to the 6th. In general, x to the a raised to the b is equal to x to the ab. What is z to the 3 raised to the 3rd? Z to the 3rd raised to the 3rd is equal to z to the 3 by 3, which is equal to z to the 9th. 0 index, x to the 3rd upon x to the 3rd equals x by x by x by x divided by x by x by x, and that's equal to 1. Or x to the 3rd divided by x to the 3rd is equal to x to the 3 take 3, which is equal to x to the 0 equals 1. 0 divided by 0 is equal to 0 to the 1 take 1 equals 0 to the 0 power. That is not equal to 1. It is undefined. Example 2. Find the value of 3/5 raised to the 0 power. Solution. We know that x to the 0 power equals 1. Therefore, 3/5 to the 0 power equals 1. Summary. The index or power or exponent tells us how many times the factor will appear in the repeated multiplication. In general, x to the a by x to the b equals x to the a plus b, and x to the a by y to the b equals x to the a y to the b, and x to the n by y to the n equals xy all raised to the n. In general, x to the n over y to the n equals xy, x upon y to the n. In general, x to the a all raised to the b is equal to x raised to the ab. 0 divided by 0 equals 0 to the 1 take 1 equals 0 to the 0 power. 0 to the 0 power is not equal to 1. It is undefined. In general, x to the n divided by y to the n is equal to x divided by y all raised to the n. And in general, x to the a divided by x to the b equals x raised to the a take b. Problems for today, page 60. taken from Mathematics in Secondary Schools in Guyana, Book 3, page 60, exercise 5A, questions 2, 4, 6, 8, 16, 18, 20, 26, 30, 34, and 38. Solution for problems given in the last lesson, page 56, exercise 4E, question 2. The scale of a map is 1 to 25,000. A. Find the actual length of a path which on the map is 1.2 cm long. 1 cm on the map equals 25,000 cm on ground. Therefore, 1.2 cm on map equals 1.2 by 25,000 cm equals 30,000 cm on ground. The actual length of the path is 30 kilometers. B. Find the length on the map of a road which is 2 kilometers long. 1 cm on map equals 25,000 cm equals 0.25 km on ground. 1 km on ground is 1 divided by 0.25 cm on the map. 2 km on ground is equal to 2 into 1 upon 0.25 cm equals 8 cm. The length on map equals 8 cm. Question A. A square drawing has an area of 4 cm squared. If the scale of the drawing is 1 to 2, what is the area of the actual object? Area A equals 2 cm squared equals 4 cm squared. Area of B equals 4 cm squared equals 16 cm squared. Or area of actual object is equal to 2 by 2 cm squared, which is equal to 16 cm squared.
The last one. If you're dividing and the bases are the same, you subtract the powers. So you're going to go out and you're going to be my young ambassadors. You're going to go out and spread the word about mathematics. You're going to tell people all about indices and how you can make 1 multiplied by itself and how you can add and subtract. Did you enjoy it?
Yes,
Julian, you had fun?
Yes, ma'am.
You learned anything new?